Hey Michelle, how are you doing?
Oh, good. How are you?
Okay, thanks. I'm not gonna turn on my video because I'm uploading some stuff for my 25 class right now for that virtual machine, so bandwidth is a
Oh,
little limited.
speaking of virtual machines, I have to ask you a question.
Okay.
Uh, so for my final project, I was thinking about setting up two Linux VMs in VirtualBox and having one attack the other using only Python.
Oh, that'd be cool.
But I only have 6 cores. So do I just assign like 2 cores to each and then leave one?
Yeah.
Okay.
You should leave at least 1 to 2 core for your host. Gonna be a little slow, but yeah, you can do that. You can use 2 core per. That should be okay.
Okay. Great.
Awesome. Yeah, I tried to do a project with the keylogger in my last 30A class, and some students they attempted it, but some students did not. Because they're like a mixed group of students, but YouTube got a couple tutorials that are pretty good for keylogger. It used a little bit of IO. I think keylogger will be like the perfect one for for multi or for concurrency, right? Like depending on how you want to approach it, because it has a lot of like input and output calls. So if you have to record everything that's right, and you can use existing Python library. So I think things like that will be really cool. Or um, you can look at different needs for security, right? Like cookie analyzer, um, you know, things like that. And then you can just write a concurrent program on it. But YouTube's, they do have some really great tutorial for that, how to use some of the libraries for the IO. I think we learned a little bit of that earlier on in this class. We talked about input, output, and so on. So basically, keylogger is just a way to read signal from the keyboard and then put it into a file. So,
Huh.
all right. So let's talk about the lab today. You're gonna see that it's gonna be very close to what we've done before. Coming back to like unit 2, where we talked about CPython or Python, right? Um, so when you use, for this particular lab, it's best to use Linux. So you can continue to use your Linux virtual machine. If you do run it in the interpreter, you're gonna, multi-thread and stuff like that doesn't simulate well in interpreter. And so CPython in particular, if you look at the interpreter for CPython, the code for it, it actually talks about GIL. And if you just Google GIL in general, you're gonna find a lot of hits about GIL being demoted or retiring GIL. But we're gonna talk a little bit about GIL as the book dedicate one chapter on it. So instead of covering the entire chapter in 1 week, I combined some of the chapters, and we're gonna try to hit it in the lab today. And so understanding GIL would be tying back to our concept with CPython. And GIL stands for Global Interpreter Lock. This is a mutex that protects access of Python objects. So when we're using multi-threads, we want to prevent other threads from accessing a certain shared resource. For example, shared memory would be the area. So in multi-threading, we want to make sure that we would apply the concept in that we want to control what resources being accessed by the individual thread. So because GIL would be allowing us to prevent the multi-threads from executing Python bytecodes at once. And so when you write your program, your interpreter would take that and convert it into low programming language or machine language. and that will be executing the instructions, right, in order to execute your program. Now, when you use the interpreter that is CPython, you can implement GIL for multi-processing or a multi-threading, I'm sorry. So the way that we want to apply GIL is that we want to prevent race conditions. And we talked about this when we talked about when we did the assignment in the lecture. And we want to protect the thread from utilizing all the resources and changing the data in the shared resource. So Python threads share memory, we know that. Multiple threads would be running simultaneously, and you can assign one core per thread. We learned that. Therefore, when we're accessing the shared data that is dependent for the algorithm, we would need to decide what thread is running, and so that way the data doesn't modify for the subsequent threads, which is what we know it as racing or accessing the data that's changed. Okay, so here it talks about what GIL is and how GIL is applied. And this is a line of code that comes from the CPython interpreter. And this was written by Guido, the creator of Python. And so for the interpreter, this particular line is where GIL happens. It does the lock of the interpreter. Now for thread safety, in thread safe code would only manipulate shared data in such way that it does not interfere with other threads. We don't want it to be impacting the other threads. And GIL was created to manage memory but it is not thread safe. So one thread is running at a time so that it will be having no race condition, but GIL does not prevent the process from running on different processor on the machine. So if you enable 3 processors, right, it's possible that other processes will be running using different processors or what we see as core. So if it's simply allowing only one thread to run at once within the interpreter, then it does prevent you from using multiple CPUs simultaneously. So it's a catch-22 concept. If we're controlling only one thread to be accessing the resource, then are we really looking at parallelism or concurrency? Now, GIL gives you the interpreter level lock. It prevents execution of multiple threads at once using Python interpreter. Each of the thread that is running must wait for the GIL to release, so that way it would be able to run. So when you are multi-threading your application, it would then simplify it down to the single thread. Now, GIL would also prevent simultaneous access of your objects by multiple threads at once. So what we want to do is we want to use GIL to be able to control how the shared resources is used, but we don't want all the threads to be using that same resources at once. So if we have GIL, then it must own to execute within the interpreter what decides that GIL should be released. That will be your bytecode instructions. So when your bytecode is compiled, then the actual instructions that interpreter uses for the execution of the application would be within that bytecode. And so when your program is compiled, for example, when we're looking at CPython, right, we say that it would be a .pyc because it's still running C in the back, or a PYO. So it might be just a single bytecode or just an import statement, whatever it could be that it would break down to the instructions for the interpreter to be able to execute your program. Now, when you're running pure Python code, then what we would see is that GIL has to be released in order to execute many of your bytecode instructions. So as it locks it for each one, right, each of the thread, it would subsequently have to release in order to complete the entire program. So if you create your code to act as a single bytecode, then GIL will not be able to release for the period of time that that statement occurs or it's running that statement. So it's designed to really work with multiple bytecodes, right? And it would then be released for one after the other. So in Unix system, this was really designed in the Unix time, right? The pythread type lock is an alias for the standard C lock. This is known as a mutex. So in the code itself, if you read the interpreter code, you would find that there is a function, actually two functions. So it has these two operations that would lock and release the lock. So what that does is it's using allow threads and unallow threads to block IO operations and unblock it. So when you enter the lock, it's going to use the begin allow threads. And when it's unlocking, it's going to use the end allow threads. And this is happening in the interpreter itself. Okay. So when you use CPython, built into the interpreter is already GIL. Okay. So a little bit of review on race condition and some notes with it. So we know that this is dependent on the sequence or timing of other uncontrollable events. And race condition sometimes is difficult to identify if they're not familiar with the problem. And sometimes that could be random or erratic and unpredictable. So we talked about race condition can happen in hardware and software. And so when you're using Python, right, we want to have an expectation that race condition could occur when we are implementing concurrency. So this is why GIL is essential for Python, but there has been discussion that GIL should be removed. Okay, so if they turn that off, and I guess in development world for Python development, there is upcoming, right, operations that's going to be able to handle what is equivalent to GIL. Okay, but it's not fully accomplished and tested. So we will see that down the line if they decided to remove GIL. So this is still being in discussion, and it's been a few years now that they have talked about this. Okay, because it really defeats the purpose of implementing concurrency if we keep having GIL, because the interpreter would then having to lock, right, the process and unlock the process, or lock the thread and unlock the thread. So subsequently, it would make it more unsequential than concurrent. So just to review, as we're also working on our project, concurrency versus parallelism. So concurrency really defined the problem, where parallelism defined the implementation. And so there are many solutions in how you would be able to achieve this, where you can use standard threading for asynchronous programming, or we can do process forking, in that when we are doing multi-processes, right, you can decide on how each of the process is going to be executed. So when you use processes or threads, we would then be able to implement timing on how you want your algorithm to be ran. And so keeping in mind that there is GIL in the back, we want to make sure that we think about what is achieved in our program. So here it talks about how you can implement threads, and if you create the thread, okay, so it's whether it's interpreter thread that's called a green thread, or if it's OS, that will be your native thread. Okay, so we can boot up our Linux virtual machine, and you can enable multiple processors, multiple cores on your virtual machines. You can just assign 2 is good. Okay. And in this one, we're not going to hard code in the timing. We're actually going to use time command in Linux. So let me log in here. Okay. So for the step 3, we are going to use Nano to write our program. So we're going to do open up your terminal. And we're going to Nano in, I believe I call it benchmark thread benchmark. So we will issue the command nano thread benchmark.py. Okay. And that will bring you to Nano. And you would have, of course, nothing there yet. So you can enter the code, and this is going to look familiar to you because, sorry, I have a typo here. All right. So let's look at the code, right? We are going to use random module. So we import in random. We are going to use threading module, and we're going to use the superclass thread. So we're going to import that in. We're going to use multi-processing module, and we're going to use the superclass process because we are going to create a pool of threads and a pool of processes. We have a variable called size, and this is going to give us the number of random, the amount of random numbers that we'll add to the list. And for our threads, we're going to use 2. You have a list called myList. Then next is going to be a for loop. We would have, we would append, right, all the value in myList. Okay. So basically you have random numbers that's going to append to myList. The first function is called func. And in that, we are going to simply append random numbers. Then we have a second function called multithreaded. And here is where we would implement the multithreads. We have a job list, and then we would loop to create our thread. So the thread object is then initialized here, and that would be part of the thread class. We would target the func method, right, as we define that right above it. So that's like what we've been doing in the last few weeks. So then it's going to append the thread into the job list. Then we'll start the thread, and since we have multiple threads, we would have a for loop for the start and a for loop for the join. So join simply allows us to wait for the thread to be finished. Now, this is when we multi-thread. The second one is when we want to just simply use it as a sequential synchronous program. So the third function is called simple. And in this function, we have a for loop that's going to call func, and that's going to be using these arguments to be able to append the random numbers into my list. And then the fourth function is called multiprocess, and this is where we would use multiprocessors to be each one to execute, right? We have a pool of processes, then we have a loop similar to what we've done with the thread. We are going to have use the loop in order to generate each of the process and store it into the process pool. So that's what we've done here in this for loop. So you create a P object, which stands for process, and that is a process object, and we're going to target the function func. Okay. Then we have another for loop to start our processes and a second for loop to join or to wait for each process to finish. Then the last part will be our main. So this, make sure that we know it's double underscore. So if namespace is main, then we are going to call multi-threaded. So that's going to be first. And we comment out the other two calls because we want to run the timing on it individually. So you're going to run the multi-threaded first and get the time. And then you're going to comment it and then uncomment simple and run and get the time. And then we would do multi-processes last and we can compare. Okay, let's come back to our code now. Any questions regarding the script? Mostly review, right? You've seen this before from unit 2 all the way up until now. So once you have done, you have entered your script, you can do Control X, yes, and enter to save. As I didn't change anything, I just exit there. And then we would call on the time command, and we would do a Python 3 command with that as an option. And then we would call thread benchmark.py. Hold on one second. Let me check my comment to see if I have everything I needed. Okay. Let's undo that and comment that out. So let's save that and rerun that again. So when you run, you can use the time command with the Python command and then your file name. So here it tells us the time, right? Your real is going to be 0.2803 seconds. The system would be 0.22255, and the user is 2.326. So this is for multi-threaded. Okay. Now coming back to here, right? We want to record the time output. Then what we're going to do is we're going to comment the multi-thread and uncomment simple next. Okay. So for the next step, what we're going to do is we're going to come back to the file, go down to the bottom, and we want to comment out multi-threaded and then uncomment simple. So we're just going to run it with just simple. Then we're going to save it. And then we're going to time it again. So here with just a sequential approach, we would see that it gives me the real time as 2.659 seconds. The user is 2.363 seconds, pretty close to the previous for the user, but you want to look at the real time. And then the CIS is going to be 0.295. So when we go from multi-threaded to sequential, we can see that it is definitely faster. Actually, yeah. For the user side, it's about the same, but if you look at the real-time comparison, right, it's slightly faster than multi-threaded. Because of GIL, right? When you implemented multi-threaded, that's what I'm trying to show you is that when you implement the multi-threads, it's still going to have to release that lock at the low level in order for it to be able to pick up the next thread. Okay. Then after we compare this with this, right, we would then go back and edit it again. And then we want to comment out simple, and we want to uncomment multiprocess. So now we want to see multiprocessor, how that will be. Save. Oh. Let me redo that again. Did save. Okay. Then we want to time it. So we can see that the real time, the first time I ran it, right, you see that it's lower. Now the second time that I ran it, it is 1.04. Let's try that again. Yeah. So it should be 1 point something seconds, and I'm using 4 core. So when we compare this to the multi-threaded program, right, if we only use it as a multi-threaded program, right, parallel is faster. So the deficiency is that if we implement the multi-threaded program, it might be even equal or slower than sequential. But if we implement it as a multi-process program using the multi-process module, right, then we would see that it's a little faster by about 1 second. On the user side, you see it's going to be pretty close. So we don't look at the user time, we look at the real time. And the book talked about that, chapters talked about that from the beginning. So as you uncomment and uncomment the multi-process and ran that, right, you want to compare that with the sequential and the multi-threaded approach. Okay. Any question regarding part A? So last week we spent a little bit of time doing, HTTP requests. And so I want to come back to the multi-threading for HTTP requests. With part B. So part B contains a very small program. And when you work on part B, you would use Nano to write your program. So if we look at the code, it starts with two import statement. We are going to use threading module and we're going to use requests because requests, right, for HTTP. We have a list called URLs and we have a function for called worker. And we're going to have a while statement that's going to be in the while statement. We're going to nest try and accept. So we would try URL we define here as a variable that's going to be, it's going to pop. So it's going to remove from the URL list. And then we want to, right, basically catch the index error. Then we have a break statement. Then we are going to use the get method from the request library to be able to obtain URL. This right here is just do for I don't, that would be more like you can use a variable or just a like a space. Okay. So for I in range 10, we are going to have 10 workers. Okay. And we create a thread or T object that will be a threading object. And our target is going to be worker, which is the function that we define here. And we're going to start. Then once you have the file written, you're going to save the file. So in this program, the threads would drop the GIL while waiting for each of the socket operation to fetch the URL over HTTP. And as they do that, they're going to finish the work sooner than having a single thread. Okay. So if you wanted to run it as a sequential program, you simply just call the function def worker, right? Call the function worker. But since you create the thread, then you would start that thread, and that thread, each of the thread is going to target that function. So the time that you're going to get is the multi-threaded program time. If you really want to compare that like the last program, then you can just add the function call and going to comment out the threading. Okay. So coming back here, we are gonna go ahead and do Control X to save. Yes, and enter. And then we're gonna do a time Python 3 http threads.py. And significantly, we would also see that it will be fast. Okay. So we would have the real time showing here that it's about 0.373 seconds. A third of a second. So after that, what you will do is take a screenshot of your program output showing the time. And what can you conclude about GIL? And I have given you a lot of details about GIL from before entering the procedures. So think about how the multi-threads are being implemented and what GIL is used for. So explain how is GIL impacting the multi-threaded program. So in the URL program, the HTTP program, we see that the GIL was dropped. So it doesn't have any kind of slowdown, right? That's why I put the note there for number 14 is that when it was waiting for the socket, it dropped the GIL. And so when it fetches the URL, it was able to achieve that sooner simultaneously. Compared to the first program, we saw that when we ran the multi-threaded, it was slightly longer than the sequential in that it has to wait for GIL to release the lock so other threads can use the resource. And resource can also be CPU and shared memory. Okay. Any question on part B? Okay. Let's come back to here. Our lab is generally pretty short, so for today. All right, in part C, we are going to look at parallelism and GIL. So entering that, I put that, what if your task will finish sooner only by running Python code simultaneously? And what we can do is we can scale it for parallelism, and GIL would prevent that. So you have to use multi-processes. That way it would require a little bit more of your storage. So because remember, we talked about having multi-processes, each of the process will require its own space. And compare that to threading. Threading, we are able to share memory space. So you will be able to gain better time or have better time, gain performance, but you're gonna lose space, right? And that comes back to what we talked about at the beginning. So in the program, we're going to fork 10 processes. And the processes would run in parallel in the cores that you allocated for your virtual machine. So when we compare that to having one core to multiple cores, the program, we would say that it would not run faster with 10 threads than with one, because only one thread can execute Python at a time. Okay, so we're going to fork 10 processes on this one. Now, each of the fork process will have separate GIL, so it doesn't require the release of the GIL for all the other processes. So that's why you're able to run faster. So here it says, because each fork process has a separate GIL, the program can proceed to work out and run multiple computationals at once. And so comparing that to other interpreter, you can take a look at Jython or JPython, right? Iron Python, which provide a single process parallelism. But CPython so far is the best in compatibility. And so there are other solutions for Python, right? However, we would then think about how these solutions are going to be compared to what is in existence in CPython. Okay, so for the last exercise in the lab, we're again going to go back to our virtual machine. And we're going to make a file called parallel GIL. And we would write our code in that file. And we've seen some of this from our prior class and other exercises. We would use OS and sys. So system module and OS module. Remember that GIL, right, is at the low level. So you want to be, so we talked about how there is native thread for your process. Okay, so that's why we need to implement these. So you have a list called nums, and you can use it like this, or you can use the I in that. So one for I in range, and we can say this many. We're gonna take, right, the length of our list, and we're gonna floor divide by 10. We're gonna have another list called readers. So when you floor divide this, you're gonna chunk it into, you're gonna group them into chunks. Then we define what a chunk is. And so that will be, sorry, your numbers is gonna be the chunk size of the nums. Okay. And we touch a little bit on reader and writer, right? As example, when we worked on this in the lecture. So using OS and sys, so for the OS, we're able to pipe And we will pipe with the reader and the writer. Now, then we need to fork for the 10 processes. So here is where we would use the fork method. Then what you can do is you can append that into the readers list. Then we are going to find the total or the subtotal by using a loop. Okay. So that will slow down. So as it goes, it's going to add it. Then we're going to print our subtotal. And that would be just be for the number, the values there. Okay. Then we are going to have that store or store, and it needs to encode it, okay, as a string. And then we're going to exit. So now this section is going to be for the parent process. So we are going to have a total is initialized at 0. We're going to have a loop for readers. And as it read it, we want to decode it and convert it into integers. So we parse it into integers here and store that into total. So remember earlier, you store everything as string. It is encoded. Now you have to decode it and you have to make it into numbers. And so your total is going to be the subtotal added, and we will print the total. So when you handle it like this, you are already converting some of the operations at the low level in your code. Okay. So let's look at the program. Then we are going to save this. And then we can time it. Okay. So here it gives us the subtotal and then the grand total, right? And then the time. So it took less than a second to be able to give us that. Since we have 10 processes, right? They simultaneously working as each of them has their own GIL. And so we were able to achieve the grand total at a faster speed. Better performance on this one. So definitely more advanced approach compared to what you've seen in just a normal processing when just randomizing and adding up, right? So we can be able to create your process and fork it. So you would then subdivide your processes into other processes and be able to achieve them simultaneously. The downside of this is that it does take up space, and you can see that in the code that we have to write it. So we have to parse, you have to write it, and then you have to read it from the area that it's stored for each one. So it takes up the memory location. And as each of them have individual location, it's able to retrieve it quickly. Okay. So after we put that in, we would save the file, then time and run the file. Take a screen capture. And then you can just briefly describe how the multiple processes are being implemented in the program. And here we saw that it was, we would then be able to use fork processes, and we know that it's 10, but the processes are then used as readers and writers, right? As what we talked about in our lecture. So as it writes, it's able to read it. Okay. And from that, what can you conclude about GIL in parallelism? We talked about how each process has its own GIL. Okay. And if you're using parallel processing, right, how would you approach that? Think about that when you write your project. Any question? Okay, so that basically covers all the 3 parts for our lab. So today we looked at how we would compare, right, sequential, multi-threaded, and processing program, and be able to time that. We also looked at how that would be written for web requests using multi-threaded program. And then we also looked at parallel processing program. And with those, we have discussed, right, how GIL is used in the interpreter with different approaches. Okay, any question? Okay, so for the submission, just need to provide screen capture and then question and answers on one document. And you can submit that on Canvas. It is not due until Sunday. So if you finish it today, you don't have to worry about it over the weekend. There's no school tomorrow because of Veterans Day. And so I hope you are able to relax and have some fun time tomorrow, right? Most of you don't have Fridays, but I will still be working on Friday, and I'll try to catch up with your grading and things like that. And then next week, I will put together or turn on your final review document. And so we will still have one more lecture next week on patterns, and then we will go into final review in week 14. I'll give you 15 that will be dedicated to your own time working on your project and preparing for the final. And then final exam will be turned on in week 16. You will have from Monday until Wednesday to complete your final exam. It's multiple choice, 50 questions. Okay. Any question?
Professor, I have a question regarding the first part of the assignment.
Okay.
So I noticed that when I run my program for, let me see, I think it was multi-threaded, and yeah, it was significantly slower than yours, and I was running on 4 core 2. So I was wondering why it would be slow on my end compared to yours.
So it's also the state of your virtual machines too, and the RAM. I think I dedicate like about 2 gig for the RAM. And then let me double check on mine. I'm pretty sure I have 4 core. Let me check. Okay, let's see. Yeah, so I have 8 core, and then I have 4 core dedicated. And then I have I think, yeah, for my RAM, I have only about 2 gigs for the virtual machine itself. But so are you about the same spec that I am?
Yeah, so I definitely have 4 core, and I think I have about the same for the memory too, 2048.
Yeah, so then it will then come back down to your hardware, right? That will be like the type of memory speed, the processor speed. So on mine, let me see. Yeah, I'm on an i7. I think mine is like 10th generation. Yeah, mine is an i7 10th generation. So that will be like an architecture base. So I'm at this per core. And so as you can see, so if it's like roughly about the same, then you can be, and through software, you would see that it is a little slower and because it's software dependent, but I think it might be just down to like the hardware level. So if you're on like even though it's an i7, but if it's a different model, yeah, they do clock at different speed, you know that. So when you're looking at like i7 or i5, right, different generation, could be in the same generation, but different models, also clock, they benchmark at different speeds. So, and then you have to consider your RAM, because VirtualBox use mostly RAM storage, right? Like how your RAM speed would be. So if I'm on a 16 gig, but my RAM speed is like, let's say 3333, like 3,333 megahertz, that is a little bit different than yours. It might be at a different frequency. So you have some variance in that in consideration. So when we benchmark these things, I think the authors, they talk about that, like we don't really consider other factors that would be hardware related.
Okay. I see. I also have a question regarding what is being offered in the winter.
Okay, hold on one second. Let me stop recording.